We humans have long dreamed of exploring the vast expanse of the cosmos. We have gazed at the stars for millennia. We wonder about our place in the universe, yet there is another frontier, perhaps even more tantalizing than space, the frontier of time. The concept of time travel, of journeying to the past or leaping into the future, has captivated our imaginations for centuries. Could we one day build a time machine and rewrite history or glimpse into the future? The answer, as with many things in the realm of science, is complex and lies at the very edge of our understanding. This essay delves into the fascinating world of time travel, exploring the science, the paradoxes, and the sheer wonder that surrounds this captivating concept. We will embark on a journey through the history of time travel in human thought, from ancient myths to modern science fiction. We will delve into the mind-bending world of Einstein's theories of relativity, where time is not absolute but rather a fluid dimension interwoven with space. Most importantly, we will examine whether time travel is merely a product of our imaginations or a potential reality waiting to be unlocked. Fasten your seatbelts and prepare to journey through the cosmos and through time itself as we explore the tantalizing possibility of time travel. Our exploration will lead us to the edge of known physics and perhaps even beyond, into the realm where science fiction blurs with the boundless possibilities of the universe. The allure of time travel is not a modern invention. Our ancestors grappled with the concept of time as a river, sometimes envisioning the possibility of navigating its currents. Ancient myths and folklore are replete with tales of time-bending exploits, hinting at a timeless human fascination with altering our temporal reality. However, it was H.G. Wells's groundbreaking 1895 novel, The Time Machine, that truly ignited the public imagination with a vivid and scientifically plausible depiction of time travel. Since then, time travel has become a staple of science fiction literature, film, and television. From the time-traveling DeLorean in Back to the Future to the cosmic wormhole journeys in Interstellar, these stories have explored the paradoxes, possibilities, and potential consequences of manipulating time. These narratives reflect our enduring curiosity about the past, our anxieties about the future, and our fundamental desire to understand our place within the grand tapestry of time. The enduring popularity of time travel in fiction speaks to a deep-seated human desire. We yearn to right past wrongs, to glimpse the future, or perhaps to simply experience the thrill of witnessing history unfold firsthand. While these fictional explorations often take creative liberties with scientific principles, they often serve as a springboard for real-world scientific inquiry, blurring the lines between science fiction and cutting-edge theoretical physics. To comprehend the scientific possibility of time travel, we must first venture into the mind-bending world of Albert Einstein, whose theories of relativity revolutionized our understanding of space, time, and gravity. Prior to Einstein, physicists viewed time as an absolute, an unchanging backdrop against which the events of the universe unfolded. However, Einstein's special theory of relativity, published in 1905, shattered this Newtonian notion, proposing that time is not absolute but rather relative to the observer's frame of reference. One of the most startling implications of special relativity is time dilation, the phenomenon where time slows down for objects in motion relative to a stationary observer. This effect becomes more pronounced as an object approaches the speed of light. For instance, if we were to send a clock on a high-speed journey through space upon its return, we would find that it would be slightly behind an identical clock that remained on Earth. This difference in elapsed time is not due to any mechanical malfunction, but rather reflects the fundamental nature of time itself. Einstein's general theory of relativity, published in 1915, further deepened the mystery of time by linking it inextricably with gravity. General relativity proposes that massive objects, such as stars and planets, warp the fabric of space-time around them. Much like a bowling ball placed on a trampoline stretches the fabric. This warping of space-time is what we perceive as gravity. The more massive the object, the greater the distortion of space-time, and the slower time runs in its vicinity. Section 4. Wormholes, shortcuts through space and time. Among the most intriguing concepts to emerge from Einstein's theories of relativity is the possibility of wormholes, theoretical tunnels that could connect distant points in space-time. These cosmic shortcuts, also known as Einstein-Rosen bridges, arise from the equations of general relativity, which describe how gravity warps the fabric of space-time. Imagine a sheet of paper representing the fabric of space-time. Now fold the paper in half so that two distant points touch. A wormhole, in essence, would act as a bridge or tunnel through this fold, providing a shortcut between these otherwise distant regions of space-time. While wormholes remain highly theoretical, their existence is not strictly prohibited by the laws of physics as we currently understand them. If they exist, wormholes could potentially allow for faster-than-light travel, enabling journeys to distant stars and galaxies that would otherwise take millions or even billions of years. Perhaps even more tantalizing is the possibility that wormholes could act as gateways through time, allowing us to journey to the past or future. However, before we get carried away with dreams of time-traveling adventures, it's essential to acknowledge the significant challenges and uncertainties surrounding wormholes. Their existence remains purely theoretical, and even if they do exist, harnessing their power for interstellar travel or time travel would present formidable obstacles that could well prove insurmountable. Section 5. The enigma of exotic matter. One of the most significant challenges associated with wormholes lies in their inherent instability. According to general relativity, a wormhole would collapse instantly upon its formation unless it were propped open by a form of matter with bizarre properties known as exotic matter. This hypothetical substance would possess negative mass-energy density, essentially meaning that it would have less than zero mass and exert negative gravity, pushing outward rather than pulling inward like ordinary matter. While the concept of exotic matter might sound like something straight out of science fiction, there are hints from the realm of quantum physics that it might not be entirely implausible. The Casimir effect, for instance, a strange phenomenon observed at the quantum level, suggests that the vacuum of space is not truly empty, but rather teeming with virtual particles that pop in and out of existence. These virtual particles, although fleeting, can exert a negative pressure, potentially hinting at the existence of negative energy densities, a key characteristic of exotic matter. However, even if exotic matter does exist, harnessing it in sufficient quantities to stabilize a wormhole would be an astronomical challenge, pushing the boundaries of our technological capabilities. Section 6. Can we make a wormhole? The creation of a wormhole, even if theoretically possible, would present an unprecedented engineering challenge, dwarfing any technological feat humanity has accomplished thus far. The amount of energy required to warp space-time to the extent necessary to create a traversable wormhole would be staggering, likely exceeding the total energy output of our Sun over its entire lifespan. To put this into perspective, imagine trying to fold an entire continent in half using only your bare hands. The task seems absurdly impossible, and yet that is essentially the scale of the challenge we face in attempting to manipulate space-time to create a wormhole. Furthermore, even if we could muster the energy required to create a wormhole, ensuring its stability and navigability would be another Herculean task. The precise manipulation of exotic matter, assuming we could find or create it, to hold open the wormhole's throat and prevent its collapse would require an unfathomable level of control over the fabric of space-time itself. It's akin to trying to thread a needle with a beam of light while riding a roller coaster on a vibrating platform. The level of precision and stability required seems almost laughably beyond our current capabilities. While the creation of a traversable wormhole remains firmly in the realm of science fiction for now, the very fact that we can conceive of such a possibility within the framework of known physics is a testament to the power of human imagination and our insatiable thirst for knowledge.